Listen, a quick recap of hyperconjugation. A hyperconjugation is something where you have sigma electrons being breaking to make a support of a pi bond. So temporarily there is a loss of sigma bond and there is a pi bond generated. And because of the loss of bonding between carbon and hydrogen, it is also called as no bond resonance. The resonating structures for the same will be like this. So you can see this is the hybrid form of hyperconjugation, which implies more the number of alpha hydrogens, more is the amount of hyperconjugation, and more hyperconjugation leads to more stability. In case of carbocations, the type of overlapping what you would notice is between sigma and p empty orbital. That means carbon having positive charge has an empty p orbital, and then you are breaking this sigma bond and converting into a pi bond. So the pi bond formation is because of the overlapping of sigma and sigma bond breaking into pi bond into p empty orbital. And we learned the idea that as long as you have a alpha hydrogens, more the alpha hydrogens, more is the hyperconjugation, more is the stability. Okay, these were all the cases we discussed. In general, if you're talking about the stability of intermediates, your first priority should always be resonance. That means always give more priority to resonance over hyperconjugation over inductive effect. And we did discuss these cases as in how many number of alpha hydrogens each possess. Based on that, you could notice we decided what is the stability order. Here, in the case of F, this is only one case where there is resonance observed. And even though you do not find lot of alpha hydrogens here, still priority wise, that is the most stable form compared to the others. Okay. Now, as we extend the hyperconjugation, we would notice that it is also been observed in free radicals. Like if you have ethyl radical CH3CH2 dot. Now, by structure, okay, I want all of you to write it simultaneously. So by structure, you can see we have H, H, and H with CH2 dot. Okay, so this dot is also again on an orbital, pure p orbital like this. Okay, you could write this hydrogens in this form, that there are two hydrogens, just to show the geometry also. Okay, now how would this participate in resonance? You know, if I take this structure, copy this, keep it here, and now break the bond on this side here. So like this and like this. This is called homolytic cleavage. That means you're breaking the sigma bond equally. And because of this, what you would notice is there is no bond between carbon and hydrogen. Instead, there are dot and dot now. And it is this dot and dot which both interacts to eventually convert that into a double bond formation. So here now I can show the hydrogens in this particular form as if it has two hydrogens. Now it has like empty orbital with single electron orbital, but it is a pure p orbital, and this is H dot. Now here it will start making a pi bond formation, and that's how the hyperconjugation is leading to formation of this pi bond formation. Okay, so generic way of representing hyperconjugated structure here is like this: H C H double bond CH2 with a H dot. Similarly, I can have H C H H double bond CH2 dot and H C H H dot double bond CH2. These three are the hyperconjugated structures, everybody. These three are the hyperconjugated structures. So logic is the same. More the number of alpha hydrogens, more is the hyperconjugation. So hybrid wise, how does it look like? It is as if it is more easier to break this bond, and then there is a partial double bond character between CH2 and this one. Okay, so this is how the hybrid looks like. All good. Now, what is the type of overlapping here? You can see the type of overlapping. What it is showcasing is sigma trying to go towards P half filled. That means a P orbital which is half filled orbital. This is the type of overlapping. If it was completely empty, that would have been carbocation case. Now you have half filled. Now the logic is the same. More the number of alpha hydrogens, more is the stability of radicals. So quickly check out these cases here at the alpha. So as you can notice here in the first case alpha, how many, in case of A, how many alpha hydrogens we have? 9. Here we have 6. Here we have 2. So that clearly makes A to be more stable than B than C. Likewise, if you compare A, B, C, D, E, F here, A, B, C, D, E, F, what is the number of alpha carbons here? So you can see here there are 2 of them. Here we have 3 and 2. Total 5 of them. Okay. And here on this already there is a double bond present on it. Clear? On that position, if you want to check out alpha hydrogens, we should not be counting it. Hmm. Now on this stage we have 2 here and 1 here. Total 3. And here we have 4.
So
And
why
here
are
we
you
have
not
2.
counting the hydrogen in the C figure?
Basically, on this carbon, there is already a double bond. Is it possible to get one more double bond in this ring structure here? No, right?
Mm. Mm.
So therefore, here no hyperconjugation type can occur on that.
Thank you.
Okay. So based on that, if you compare the stability, notice whether there is any resonance observed in any of the case. Yes, there is one case here, there is resonance, and another case here, there is resonance. At these two cases, we can see the radical can undergo resonance stabilization as well. And of course, B has more alpha hydrogens also, which makes B more stable than F. And thereafter, we have to just check the number of alpha hydrogens. So E has more than D, and then A, and last comes C. This is the order of stability. Everyone, please do check. So I'm writing that here. B, F, E, D, A, C. Now listen, more often in JE questions, instead of just asking stability specifically in the case of radicals, you would be asked what is the bond dissociation energy of CH, various hydrogens here. You might be asked like for this hydrogen, sorry, here, for this hydrogen versus this hydrogen versus this hydrogen versus this hydrogen. If at all you are breaking all these hydrogens, then what is the bond dissociation energy? In simple terms, the one which is more stable, that means it is most likely to break more easily. Hence, we can say B is least energy required, then F, then E, then D, then A, then C. Okay, clear? So this would be the bond dissociation enthalpy of various hydrogens. Um, I hope all of you got this point. Sorry. See the next case, the hyperconjugation in alkenes. How does it happen in alkenes? So across the alkene, you need to check out both the carbons together. On the left hand side or on the right hand side, how many number of alpha hydrogens do we have? That counts for the hyperconjugation. Okay. So for instance, here for this bonding, how do I show that? It is like carbon, uh, trying to break a bond here like this. It has, imagine a bond having here, here, and here with these three hydrogens here. So you're trying to break a bond with this carbon so that we can support it to double bond CH2 here. So you're in a way breaking this bond, trying to push these electrons here so that this pi electrons can move further. So in short, if at all I have to put the hybrid, it is like this. Uh, CH, I mean before hybrid, let me show you the bond types here. So suppose if you have like this, you'll get this as H plus, then double bond CH, and pushing that pi electrons onto the last carbon, making it at CH2 minus. Like this again, you can get three more structures here. These are all the hyperconjugated structures. So this is the first one. The second one includes H, C, H, and H plus, double bond CH, CH2 minus. Likewise, I can have H, C, H, and H, double bond CH, CH2 minus. Lastly, if at all I have to put the hybrid, you have to put all the dot bonds here, and then there is a double bond formation here, and then there is a double bond lost here to get this as delta negative, delta positive, delta positive, and delta positive. This is the hybrid form. Okay. Now, what is the type of overlapping we are noticing? Basically, you are breaking the sigma CH bond to make an overlap into a pi star orbital of C double bond C. This is the type of overlapping what you are noticing. In short, see, if I put it in the form of an orbital, this is what is exactly happening. Carbon, and it is having an orbital like this. One second. It is having some kind of an orbital here like this. Let's say this is how the original orbitals are. And here carbon, the next part of carbon here, and carbon here, it already has a pi bond on it like this. There is an existing pi bond. Okay, so you can see this is where the pi bond is like this. But what we are forgetting, wherever there is a pi bond, there is always a pi star orbital present like this. This is the pi star orbital. And as you try to break the hydrogen bond here, you can see, suppose if the hydrogen is present here, this is hydrogen. And as you break this hydrogen bond, these electrons will have much closer access towards this pi star orbital. That's how it initiates. So it breaks this sigma bond and tries to support into this pi star orbital. And that's how you can see the type of overlapping observed. Okay. So from there we can say more the number of alpha hydrogens, more is the amount of stability. So more stability, which implies. Everybody clear with the part? So alkenes can also show hyperconjugation in this form. So what have you noticed something that wherever there is a double bond, the adjacent carbon has to be sp3. That's a very important condition. Okay, this has to be sp3 carbons only. So as long they are sp3 carbons, then only they will show hyperconjugation. So notice this cases here. So if we compare A, B, C, D, how many number of alpha hydrogens do we have here? So clearly you can notice uh, 3 here, 3 here, okay, and 2 here and 2 here. So in total, how in short, how many do we have here? 3 and 3, 6 plus 2, 8 plus 2, 10. So total number of alpha hydrogens in this case are 10. So there are 10 alpha hydrogens. Likewise, here you can see this position, okay, this position and this, right, this and this position. So how many do we have here? Total 4 of them. Likewise, here you can see 3, here you can see 2. So based on the given pi bonds, which one is more stable here? So we can say A is more stable than B is more stable than C than D. This is how the stability varies. Now, this is a very peculiar case, that is how to compare isobutylene cis and trans. Why it is very critical case is if you compare the number of alpha hydrogens. Here also we have 6, 6 and 6. When the alpha hydrogens are all same, correct? In that case, how do we access the, or how do we assess the stability? Try to write the hyperconjugated structure, you will get a better clarity. See, when you write the hyperconjugated structure, basically you are making a double bond here, leaving behind H plus, and this carbon CH2, you are making it as minus. So this is the isobutylenes carbanion. Second case also, if you notice, you'll get minus here, double bond here, and H plus here. This is for second case. Third case, you will have minus here, double bond here, and H plus here. This is the way you can write that. Correct? So you are breaking out that H plus bond here. Now notice at what position carbon is when it is at 1 degree, 2 degree, and 2 degree. 2 degree means carbon connected to only one carbon. Here carbon anion connected to two carbons. Here carbon anion is connected to two carbons. And in general, going ahead, we'll learn it again. In general, carb anions are more stable at a 1 degree position. So carb anion stability, if you compare, CH3 minus is more stable than 1 degree, more stable than 2 degree, more stable than 3 degree carb anions. Hence, if we compare these three, which one seems to be more stable in the hyperconjugated structure? First one. And that's the point you need to catch up. Because it is more stable, the reason you will find out here, A is more stable. And between cis and trans, you just need to check out the van der Waals repulsions. Cis would have two bulky groups on the same side, making it more repulsive. while trans will have less repulsive groups. Hence, A is greater than C is greater than B. This is the order of stability. Important case, everybody, isobutylene, cis 2-butene, trans 2-butene. When you compare, stability is ACB. Clear? The reason is clear, everybody. Next one. You notice that this is called toluene, right? Ethyl benzene. This is cumene, tert-butyl benzene. In all these cases, have you noticed this carbon and this carbon is holding a double bond? And adjacent to that is a carbon having sp3. So this is an sp3 carbon, sp3 carbon, sp3 carbon, and sp3 carbon. And if you highlight all those four carbons, the number of hydrogens we have is 3, 2, 1, and 0. So despite having a strong plus-I nature here because of so many methyl groups here, this does not give any hyperconjugation. Hence, it does not show hyperconjugation, means stability wise it is least. So most stable one is A, then B, then C, then D. This is the stability order. Likewise, if you compare alpha hydrogens in this case also, okay, from benzene here, I mean, if you compare this double bond, this CH3 is trying to give hyperconjugation, a double bond character pushing towards this side. Okay. Now what happens is as it pushes electrons, this minus can move and come here due to resonance. Same way, if you put this minus here, it can come to minus charge here. So in a way, CH3 is pushing electrons to benzene ring. This CH3 is also pushing electrons to benzene ring. So both will negate each other. While here, pushing is from this end, carb anion will be here and here. But when pushing is from this end, carb anion will be here and here. It will start making resonance this way. Therefore, their resonance is not hampering the hyperconjugation. And that's the reason why you will notice B to be slightly more stable than A, then, sorry, A, then C. This is the order in which the stability varies. C will have the least amount of stability comparatively because hyperconjugation is happening from here, 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 and here. But in this case, hyperconjugation is kind of clashing with each other. Okay, clear with these cases, everybody? So wherever there is a double bond case, I think you should be able to figure out how the hyperconjugation is present. Right. So the next type is sacrificial hyperconjugation, which means sacrificial as in you are supposed to count the number of bonds in a normal Lewis structure and then in a hyperconjugated structure. For example, this is our original normal structure, Lewis structure. Can you count the total number of bonds here? You can see 1, 2, 3, 4, 5, 6, 7, 8, 9. So total number of bonds including sigma and pi are 9. Now when you write the hyperconjugated structure, because can you see this is an sp3 carbon having a hydrogen adjacent to the double bond carbon. So definitely we can expect a hyperconjugation structure. If I write the hyperconjugated structure, see how many number of bonds we have now. See 1, 2, 3, 4, 5, 6, 7, 8. So total number of bonds present are 8. Okay. So number of bonds present are 9 here. Number of bonds present here are 8. So sacrificial hyperconjugation suggests that we have uh, one bond being sacrificed. That's why it is called sacrificial hyperconjugation. Next one, and sacrificial hyperconjugation is specifically observed in a double bonded case. Remember that. Okay. Next one, isovalent hyperconjugation. Now you see, if the contributing structures and the Lewis structures both have same number of bonds. So in the normal Lewis structure, you can see 1, 2, 3, 4, 5, 6. So there are total 6 bonds. And now in a hyperconjugated structure, 1, 2, 3, 4, 5, 6. So it is still having 6 bonds. So usually observed in, okay, it is usually observed in carbocation and carbon radical cases. In such cases, you will notice isovalent hyperconjugation. Okay. While when you have carbon-carbon double bond, you will see sacrificial hyperconjugation. Next, what is negative or reverse hyperconjugation? Now you have to think it in a reverse way that an already existing carb anion which has high electron density, if adjacent to that we have an sp3 carbon which has strong leaving groups like fluorides or chlorides, then these electrons, the CH2 minus electrons, can be pushed to make a double bond, and this sigma bond can be broken to remove out those electrons with fluoride as F minus. So this is the hyperconjugated structure which you can write. Like that, more the number of fluorides, more is the amount of reverse hyperconjugation. That will provide more reverse hyperconjugation. And reverse hyperconjugation depends upon the electronegative nature. Fluorine has most of it, then chlorine, bromine, iodine. Bromine iodine is very weak in terms of reverse hyperconjugation, while fluorine and chlorine gives a much better hyperconjugation. So you can see all these cases CCl3 CH2, CFCH double bond CH2, CH3 CH double bond CH2. In all these cases, reverse hyperconjugation is observed. Now, what is the type of overlapping? Have you noticed that this lone pair is present in a non-bonding condition? That means lone pair. It is proper lone pair. A lone pair in a bonding terminology, we call it as non-bonded electron pair. So when a non-bonded electron pair, correct, makes a bond with a sigma star orbital, okay, and that sigma star is eventually converted into a pi bond formation. You know, how is that possible? Check out like this. Carbon, if you have a tetrahedral structure, this is typically a tetrahedral structure like this, isn't it? Where we have fluorine, fluorine, fluorine here. So if you notice the orbital, this is the fluoride orbital here, carbon orbital. So that carbon orbital, if this is sigma bond, if this is sigma bond, the opposite direction will always be sigma star orbital, and sigma star is empty. And here we have another carbon, clear, having an orbital which has an electrons present in it, like this. It has electrons present on it, a pair of electrons, lone pair here with a minus charge. So have you noticed this lone pair has much easier access to that sigma star orbital? So that is why it will start making a bonding overlapping with that sigma star, pushing away electrons of fluorine. And that will convert this sigma star characteristic slowly into pi bond. So that's how it will convert into a pi bond, and F minus will come out. Okay. Please remember the type of overlapping. This is a question that has been asked in GE. That is, it is between a non-bonded electron pair versus a sigma star. That's how the hyperconjugation initiates in reverse hyperconjugation. Everyone clear? Now, quickly, let us browse through the applications of hyperconjugation and other effects. The first one, more often asked, is heat of combustion. Well, heat of combustion is the energy released when 1 mole of substance is burned in excess of oxygen. So, during combustion, whatever the heat that is released is called as heat of combustion. Heat of combustion should be always assessed on the basis of first number of carbons or molar mass. If the molar mass is more, always you will find heat of combustion is more, irrespective of whatever effects it might have or not. Second, if the molecular weight is same, that means if you are talking about isomers, in such case you should check out the stability first. So if the stability is more, heat of combustion is less. That means energy released is less. So quickly notice these cases. First case, A, B, C, D. Although A is very unstable form, it is very unstable form, we expect it to release more heat of combustion. But the number of carbons are less. So because there are only 3 carbons as compared to that of 6 carbons here, so heat of combustion will be higher for D, then C, then B, then A. This is heat of combustion. Likewise, if you compare these four, now this time number of carbons are same. If number of carbons are there, same, then you check out stability. Since A is least stable, then B, then C, then D. Why? Ring strain. 3-membered has a huge ring strain. 4-membered will also have, 5-membered slightly lesser. 6 will have the least ring strain. So that's how this order. Next, heat of combustion in these three cases. In such cases, check out number of carbons 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. 1, 2, 3, 4. So obviously number of carbons are least for this one, but highest is for A. So A greater than B greater than C. So this is called a spiroform. This is a bicycloform compared to that of two isolated ring forms. So all in all, you need to just check number of carbons. Okay. Now the fourth one is an exception. This is an exception. See, what is the exceptional thing about it? See, A, B, C, this is isobutylene, trans 2-butene, and cis 2-butene. Now, if you remember the stability wise, okay, if you compare the stability wise, what did we learn? Stability wise, we learned that A is more stable than B than C. Okay, so if the stability is more, heat of combustion should be less. So usually we expect A to have less amount of heat of combustion and C has to be the most. While C is most here, there is slightly swapping between these two. So that means instead of B, now it is A, then B. So trans usually releases least amount of combustion. This is only an exceptional case. I would suggest you remember it the way it is. Okay. Based on stability, we expect that A should release least energy, but slightly I mean, it is better than that of transform. Okay. Now, this logic works on heat of hydrogenation also. Heat of hydrogenation means how much amount of heat is being released when you add an H2 molecule. Okay. So, for H2 usually gets added wherever there is a pi bond or wherever there is a cyclic structure. Okay. So, basically, you are covering the unsaturation. You are trying to fill the unsaturation towards saturation. In that case, energy will be released. That released energy is called hydrogenation energy. Hydrogenation does not depend upon how many carbons or molar mass. It mainly depends upon how many sigma bonds you have and what is the stability. So more the stability, less is the hydrogenation or less is the heat of hydrogenation. Or more is the pi bonds, more is the hydrogenation observed. Now in this case, you can see this is 3-membered ring, 4-membered, 5-membered, 6-membered. You don't have to worry about number of carbons. Straight away, you need to check which one is more stable. D is more stable, so it will release least amount of energy. So A releases most, and this is the order of heat of hydrogenation. And here also, it doesn't matter how many carbons you have, it will still be the same. Okay. And next, between A, B, C here, in this case, check out bicyclo is less stable than spiro, then isolated. So that's why this is the order. Okay. So it is all based on stability. So whatever I have written is reverse of the stability. Isobutylene, again an exceptional case. Here we will have C greater than that of A, then B. This is exceptional. Same as heat of combustion, here also it is heat of hydrogenation. Next, now notice this one, very interesting. One cyclic structure. One cyclic structure requires one H2 to open up. Here there are two pi bonds. Now when you compare two pi bonds versus one pi bond, it is two pi bonds that is always dominant. Although stability wise it is highly unstable, and this is stable due to resonance. But yet you have to count the number of pi bonds, and that is a priority always. Hence, heat of hydrogenation is greater for A than B. Here, both of them are two pi bonds, but what you notice here, they are isolated. Here, they are conjugated. Here, they are conjugated. Okay, so in that, there is one more part which I forgot to mention. Like this, if you have and double bond, which is C. Okay, and lastly, if you have a triple bond, which is D. So now, if you are comparing A, B, C, D, check it out. The A1 is called as isolated pi bonds, isolated, while the B1 is called as conjugated pi bonds. The C1 is called as cumulative pi bonds. This is cumulative. And D is called as simply alkyne. What did you notice? That all of them have equal number of pi bonds, but they do have some stabilizing nature. Different stabilities are observed. Out of these, the least stability is for cumulative form. That is the least stability. So in such cases, C will release most energy. Then alkynes will always release more energy than alkenes. And then compared to that, A and conjugated will have already enough resonance stability. Therefore, it releases least amount of energy. So this is the order, everybody. Okay, isolated, conjugated, cumulative, and alkyne. Next one, you can see this is this is conjugated, this is conjugated, this is isolated, and this is cumulative. Okay, so based on that, what are the effects you can notice? First, there is resonance, yes. So tick mark that. Second, resonance, yes. Third one, no resonance. Fourth one, no resonance. Now count the alpha hydrogens. Alpha hydrogens, if we compare, 3 here, 3 here, total 6. Here, if you compare, alpha hydrogens are only 2 which are participating hyperconjugation. Here we have 2 here and 2 here. So total 4. And here we have 2 only on this side. This side there is no hyperconjugation. So 2 here. So these are alpha hydrogens which are participating. And since resonance should be given more priority in terms of stability, and when it comes to heat of hydrogenation, that will be the least one. So out of this, definitely conjugative has the more least energy or least stability, then C, then B, and last comes A. Hello everyone, please check. Heat of hydrogenation is clear. If anybody is lagging or you feel like I'm going fast, please do interrupt me, okay? Is this all good, everyone? See the next case. Now there is one pi bond, two pi bonds, and three pi bonds. Simply on the basis of number of pi bonds, what I can say about heat of hydrogenation is D should be expected to give more, and then B because it is isolated, and C because it is conjugated, and A. This is what we expect, correct? Based on the general idea that what happens to the heat of hydrogenation. But what has been noticed is that when it comes to benzene, exceptionally, it is giving least amount of energy, even though it has three pi bonds. Even though it has three pi bonds and you add 3 moles of H2, even after adding 3 moles of H2, it will form cyclohexane, but the amount of energy released is very less. You know how much it is? If you compare B, B will be the highest here, then comes to C, and then comes D, and then A. So it is slightly greater than single pi bond, but it is lesser than two pi bonds. Even though it has three pi bonds, the energy release here will be lesser than two pi bonds. Okay, so what could be the reason? Of course, there is resonance, right? But here also there is resonance. Even though there is resonance, there is something exceptionally different thing happening in benzene. And this characteristic is what we call it as aromaticity due to aromaticity. So the idea that there is something called aromatic compounds has arisen from this point only. Okay, that suddenly we saw that benzene is been showing exceptionally low heat of hydrogenation. Okay, right. So going ahead, we will discuss that. But I hope you got an introduction towards what is aromaticity. See the next case, this ninth case, A, B, C, D, E. Again, you will notice whether there is resonance happening or not, and whether there is any alpha hydrogens present or not, and how many are there. So first resonance, yes, yes, no resonance, no resonance, yes, there is more resonance. So you can see the resonance is very high in the last case, E. Okay, hence stability wise. So first let me write down stability, then heat of hydrogenation. So stability wise, you can see E is more stable. Then now count the number of alpha hydrogens. That will help in the second case. Here, check it out. 3, 2, 2. Total 7. Now here we have 2 and 1. Total 3. Here we have 2, 2 and 3. 7 again. Here we have 1 and 2. Total 3. Okay. And here we have 2. These two. These are all the forms we have. Correct. So stability wise, if you compare, definitely E is more stable, then A, then B. These are all based on resonance and hyperconjugation. And then stability wise, C is greater than D. Correct? So this is the stability order. Now tell me what will be the heat of hydrogenation order. So it will be exactly reverse. So D greater than C greater than uh, D greater than C. Sorry, 1 minute. I made a mistake here. C, not D. Now notice this one. Here there are three pi bonds, 2, 2, 2 and 2. So in comparison, but this is not benzene, right everybody? Since it is not benzene, that exceptionality is not applied here. So hence E will still be the highest, and thereafter we will have D, then C, then B, then A. Correct? That's it. This is the order in which it will be. Everybody clear? Stability and heat of hydrogenation. This was a JE question, everybody. So please do remember how to place the order. Very typical mistake is that we just check the stability and reverse it. Okay. Just be careful with the number of pi bonds. See the last case, A, B, C. Just compare number of alpha hydrogens in all these cases. So how many alpha hydrogens here? So there is only one here. So alpha hydrogen is 1 alpha. And here we have 3, 3, 2, 8 alpha and 8 alpha hydrogens. And here if you notice 3 and 2, 5. So you have 5 alpha hydrogens. So clearly shows that B is more stable than C than A. So this is the heat of hydrogenation. Done. Next, see the effect known as electromeric effect. Electromeric effect is also an electronic effect observed specifically when you have pi bonds. It is a temporary effect only observed in multiple bonds, which is double bonds and triple bonds. It is a temporary shift of pair of electrons, that is pi electrons, on any one of the carbon joining atoms. One of the joining atoms, that means one of the multiple bonds existing on that position. For example, there is a double bond here. As it is, there is no shifting of these pi bonds ever. But as soon as you push this H plus in the closer vicinity of this molecule, there is a charge induction. So as soon as this observes that there is an H plus approaching, automatically this pi bond will break from here and start pushing electrons towards one of the carbons, and the other side will start getting positive charge. Now this temporary movement of pi electrons towards one carbon, this is what we call it as electromeric effect. And it is this electromeric effect which helps in making a bond formation. So this minus bond, this minus charge will go and take H plus from here, creates a carbocation. Okay, clear on that? Right. So that's how we can get a carbocation formation. Now, if the pi electrons are present on the main chain only, can you see this carbon is a part of main chain? That is, if you write the IUPAC numbering also, it is like 1, 2, 3, 4. So if the carb anion is on the main chain, then we say it is giving a plus E effect. Say it is showcasing plus E effect. Now what is minus E? Suppose if a double bond is like this, C double bond O, and then the H plus is approaching. In that case, pi bond will always shift onto more electronegative element, which is oxygen in this case. So from there, if it is taking H plus, you can get a carbocation here with carbon having a plus charge. Now this time electrons are going away from the main chain because it is 1, 2, 3, and electrons are going away from the main chain. If they are going away from the main chain, then we call it as minus E effect. So wherever you notice that C double bond O, C double bond N, C triple bond N, in such cases we show minus E effect. Okay. If you have C double bond C, C triple bond C, or if you see any benzene form here like this, in such cases, what do we say? It is showcasing plus E effect. Okay. All of you clear on that? In which case it shows plus C and in which case it shows minus C.
So can you
Right,
explain the
everyone.
plus C effect? Minus C effect.
Minus E is when the electrons are going away from your main chain. What is the main chain in IUPAC beta? 1, 2, 3. क्या इस पर्टिकुलर लाइन पे इलेक्ट्रॉन्स है अभी नहीं ना वो इलेक्ट्रॉन्स उससे दूर चले गए ओके so when they go away or away from the main chain then we say it is showcasing minus E. Okay, so to give you a quick summary, we learned that electronic effects are of four kinds: resonance, hyperconjugation, correct? Inductive effect as well as electromeric effect. Inductive effect operates only on sigma bonds. Resonance operates mainly on pi bonds, except one or two exceptions where there is sigma bond is also involved. Then we learned about hyperconjugation where it operates on carbocation, carbon radical, as well as double bond. And lastly, electromeric effect, which perhaps happens on triple bond and double bond forms. Okay. The first three are temporary, electromeric effect is first three are permanent and electromeric effect is temporary. Okay. Now, before going further into the idea about intermediates, we need to understand what are these terms, electrophiles and nucleophiles. Okay, check it out. Electrophile is a species where it has two electron deficient on it. That means it has an octet incomplete form, or octet may be complete, but it has an empty d orbital or empty p orbital like that. Since it has an vacant orbital, it is definitely electron loving species, and they are generally Lewis acids. Okay. Now these electrophiles can be positively charged, they could be neutral as well. In positively charged, these are all the electrophiles, that is H plus, CH3 plus, Cl plus, NO2 plus, NO plus, and pH N2 plus. These are all the electrophiles. Well, Na plus and K plus specifically does not act like an electrophile because these are those species which are actually more happier by releasing their electron. By giving away electron, they will attain more stability. So they do not have any urge to accept any pair of electrons further. Okay. Because their octet is just completed. Hence, Na plus, K plus, Cs plus, Rb plus, they do not act like electrophiles. Next. Check out neutral species. Neutral species are of two kinds. One where there is an incomplete octet. Other one, octet is complete, but they have an empty d orbital. Now notice these cases BF3, AlCl3, BCl3, CCl2. In all these cases, octet is incomplete. So it has an empty d orbital ready. So octet is incomplete form here. Okay. So hence this is an electrophile. Very important electrophiles. Everybody, all these are important electrophiles. Now, in p orbital syllabus, we will come visit again. There we will learn that BF3 is a weaker Lewis acid compared to BCl3, compared to BBr3, compared to BI3. So strength wise, this is the Lewis acid strength. Likewise, if you go down the group, then BCl3, okay, so sorry, BCl3, let me compare this one. BCl3 is more compared to that of AlCl3, compared to that of GaCl3, compared to that of InCl3, compared to that of TlCl3. These are all the group elements. So this is how down the group the Lewis acid nature decreases. Okay. Next one is a neutral or empty d orbital cases. So ZnCl2, SnCl2, FeCl3, all of them will have metal uh, with a polarized charge on it and empty d orbital. Now, if you notice PCl5, PCl3, PF3, all of them have empty d orbital and they are all connected with high electronegative element. That's why they have a lot of positive charge on the central atom. So SO2, SF4, SO3, SO2Cl2, SbCl5, SbCl5 or AsF5, all these cases are the ones where there is an empty d orbital, which means they all can act like Lewis acids. Okay. Here I have to write one more, SOCl2 also. SO2Cl2 as well as SOCl2. Both will act like Lewis acids and they can be used as electrophiles. Next one is neutral complete octet with a positive charge on it. For example, carbon dioxide. Carbon dioxide is neutral, there is no problem. It has complete octet, but it has polarized positive charge. and that encourages nucleophile to go and attack on carbon. Similarly, aldehyde, for instance, carbon has a delta positive charge where nucleophile will be readily attacking carbon. And same, I mean, not SO3 here. SO3 is not essential because it has empty d orbital. So we don't have to write that here. Please remove that part. So wherever you have carbon with this delta positive charge, they can still be considered as electrophiles. Now, what is nucleophile? Nucleophile is two electron donors. That means it is a pair which is donating. So all lone pair donating groups are called as Lewis bases. So they are also either neutral form or an anionic form. So you can see all the halides, NO2 minus cyanide, OH minus RO minus, all of these, R minus MgX, which means Grignard's reagent. This is Gilman's reagent. All these which has R minus, they are very strong nucleophiles as well. And along with that, if they carry any lone pair group on it, they can be always categorized into nucleophiles. So all the nitrogen containing groups, oxygen containing groups, which has lone pairs on it, they can act like nucleophiles. More importantly, if at all you have only pi bond, correct, on a double bond, triple bond, or on benzene, these pi bonds can also be used as a nucleophile because they can, that pi can act as a pair of electrons by electromeric effect. Remember, that's what we learned just now. Due to electromeric effect, these can also act like pi donors, right? Hence, these are nucleophiles. Next, there is an important term known as ambidentate nucleophiles and ambiphiles. See, ambidentate means you have two different species options. That means within NO2 minus, it is nitrogen's lone pair which is available as well as oxygen's lone pair which is available. So lone pair availability is from two different sites. So when you have two donor sites, we call it as ambidentate nucleophiles. Okay. So all these cases, NO2 minus, CN, S2O3 2 minus, SCN, CNO. All of these would have ambidentate nature. Next one is ambiphiles. Ambiphiles means groups which can act like both electrophiles as well as nucleophiles. For instance, when we discuss about carbon dioxide, we were emphasizing more on carbon. But do you know that due to electromeric effect, this oxygen can get negative charge? And if this gets negative charge, it can invite an electrophile to it itself. That means an electrophile is invited as a nucleophile is also invited. When a molecule invites both electrophile and nucleophile, you call them as ambiphiles. Usually, C double bond N, see, C double bond N, C double bond O, and C triple bond N. These are those cases where they will invite both electrophiles as well as nucleophiles onto it. Okay. Hence, whenever you see this connection, it means these are ambiphiles. Okay. Everyone, definitions are clear. Ambiphiles and then ambidentate nucleophiles and basic nucleophiles and electrophiles. Next, check it out. Resonance effect or mesomeric effect while causing on the groups. For instance, if you have C double bond C and then a group like Z is connected to it, imagine it has a lone pair on it. If it has a lone pair on it, then what it does internally is that this lone pair is being pushed here so that the resonance can take place. You can see there is a conjugation. The conjugation is lone pair, sigma, and pi bond. So definitely this is a conjugation. If there is a conjugation, there is resonance. Correct? Now, have you noticed that if I consider like this is one species and this is one the other species. So this species here is offering electrons and this species here is accepting electrons. Now the ones which is accepting electrons, correct? We call it is showing minus M effect. And the ones which is pushing away electrons, we call that as plus M group. So here Z is called as a species which is showing plus M effect, and this group is showing minus M effect. The reverse can also be true. Suppose if uh, you have something like this, I have CH2 double bond CH, and here I have CH2 plus, for example. And then if I put it like this, now this time this is resonance happening on this other side. So I can see as a group, this entire group versus this entire group, if we consider, this group is actually pushing electrons away, which means it is showcasing, you know, plus M effect, and CH2 minus CH2 plus is trying to pull the electrons. That means it is showing minus M effect. Okay, done. Now notice all these cases. These are those cases which contains at least one lone pair on it, as it is directly connected to the other species. So you can see NH2 connected, NHR, NR2, OH, OCH3. In all these cases, there is a lone pair present on it. Even halogens, all the halogens will also have lone pair present on it. Which means what kind of a resonance effect they will show? They'll always show plus M effect. If there is no lone pair and they are strongly withdrawing groups, chances are they can show minus M effect. All of these will show minus M effect. Imagine benzene as a reference species on which we are comparing these groups. So on benzene, if there is NH2 present on it, what kind of effects it is showing? The lone pair of nitrogen we can push electrons towards benzene. So I can say benzene here is pulling, that means it is minus M, while NH2 is pushing, that means NH2 is showing plus M effect. And due to NH2, the negative charge keeps scrolling around benzene at different locations. Okay. Now, any species which increases electron density on benzene, you call them as activated groups. So can I say NH2 minus is an NH2 is an activated group because it is pushing electrons towards benzene. While if you notice NO2, in the case of NO2, now what is happening? The pi bond is actually been called from benzene towards NO2. So in a way, NO2 is pulling electrons from benzene. Hence now NO2 is showing minus M effect. So due to its minus M effect, the positive charge will come here, and that positive charge will keep moving across these three positions. Okay. So I can say that all these three here, if you compare, they are trying to get positive charge on benzene. Positive charge on benzene implies that it is decreasing electron density. And such groups which are decreasing electron density are called deactivating groups. Okay. These are deactivating groups, everybody. Okay. As a small, just here, I'll just write down what are activating and what are deactivating groups here, everybody. You can also make a note along with me. So clearly, I can say NH2, right? OH, NR2, right? OCH3, and NH, C double bond OCH3, O, C double bond OCH3. Correct. All these are showing plus M effect. And due to plus M effect, they are activating. Next, if I have only CH3, C2H5, okay, and CH and dimethyl here like this, all these are, or C, sorry, in this case, all of these are showing hyperconjugation, and due to hyperconjugation also they are pushing electrons towards benzene. Last, if you have only methyl here, I can show it is showing mainly plus I, and all these are, I can say all of these cases here, whatever I've written, these are all activating groups. These are all activating groups. Clear? Now, one thing you need to be very clear, everybody, that see, if benzene is connected, just think about it carefully. It's a very important thought to have, that if there is like this benzene with NH2, can I say that this carbon's electronegativity is less than this nitrogen's electronegativity? Which means, in a way, the electrons are being pulled towards uh, nitrogen due to inductive effect. So all of these have more electronegativity than carbon, which is connected, which means they have minus I effect also. But you remember, their plus I is very, very dominant than minus I. That's why overall we say they are activating groups. Same logic here. Hyperconjugation is still much greater than that of plus I, although both of them are helping it to activate. Okay. Now, on the other hand, if it comes to rest of the groups like NO2, cyanide, SO3H, COOH, COOR, CHO, C double bond OR, like this. Now, if you compare all these cases, they are all showing minus M effect, and their minus M effect is way stronger than their minus I. Likewise, if you notice halogens, that is fluorine, chlorine, bromine, iodine, and along with that, we'll also have NO group here. Now, they are all showing plus M, but this is the only exceptional case where even though plus M is there, the minus I is more dominant. These are all with minus I dominant. Next, CF3, CCl3, right? And Nr3 plus, NH3 plus, like this, or OH2 plus. Now, in such cases, these are those cases where minus I is very high and there is uh, uh, no other stabilizing factor which you can get. Okay. Now, such type of groups, right? They are all actually pulling the overall, they are pulling the electrons away from benzene. So these are all deactivating groups. These are all going to be deactivating groups. So please keep in mind which are activating and which are deactivating, everybody. Clear? Everybody, did you made a note of all the activating, deactivating groups? Next, let's understand what is aromaticity. Let's see. When you have a pi bond, you're treating with H2 and nickel. So H and H gets added. The energy released in this case is, let's say, X units. Okay, I'm rephrasing the same thing we discussed earlier. Hydrogenation, heat of hydrogenation. Please listen to that carefully again. Let's say minus X amount of energy is released. If we have two pi bonds with an isolated form, definitely we expect 2x to be released, and practically also almost 2x is released. If you have conjugated double bonds, due to resonance, there will be less amount of energy released. Let's say minus 2x plus some r amount of energy. That means overall negative charge which is released is lesser. If you have three pi bonds, we expect 3x to release, but due to resonance stability here, there will be some plus h star lost. This much amount of energy is lost. Okay. And in this case, this is still greater than that of two pi bonds, except not in the case of benzene. So in benzene, if you add 3x2, we are expecting a similar thing, that there should be minus 3x plus A, some energy is lost here. Now, instead of using resonance as the factor, now I'll use the terminology A. A means aromaticity. And due to aromaticity, the energy is lost. And now, if you compare, it is less amount of energy even compared to that of two pi bonds. And this nature is what we call it as aromaticity. Now, to qualify into aromatic compounds, there are certain properties we need to have, correct? So, what is the properties we see? See, aromatic compounds are of three kinds. One is aromatic, anti-aromatic, and non-aromatic. So, first I'm talking about the aromatic forms. For aromatic forms, what are the properties you need to check? First, it has to be cyclic. It has to be planar, either sp or sp2 carbon. Next, there need to be a continuous conjugation. That means there should be delocalization. And it must follow something called Huckel's rule. That means the number of delocalized electrons must be 4n plus 2 pi electrons, where n is any simple integer starting from 0, which means number of delocalized electrons should be in this particular uh, interval only. That means it should be 2 pi, 6 pi, 10 pi, 14 pi, and so on. Okay. What you will lead into is a diamagnetic molecule. It will have diatropic ring current. That means the circuit should be complete. Achha, when do we say something is a circuit is complete in electrical field, or when there is current flowing? We say that if this is a starting point, wherever we are starting, let's say here we started. So from here, it has to come back to this position, isn't it? Where the voltage difference is present, current has to travel all the way from here, right, and reach here, or rather from here to reach here, isn't it? So when the current is completed, then we say it is a circuit completed. Likewise, if the resonance is happening, that means there is a movement of electron. The movement of electron should be the place where it started, it should end there only. Then we say the ring current is available. Okay. So for example, if you have straight chain, the pi bond will go, I mean, the delocalize and end here. It is not coming back, correct? So then we say there is no diatropic ring current. Okay. All these terms are clear, everybody? What are the prerequisites for aromatic compounds? Now notice, when it comes to benzene, we say it has two structures. One is this way, the other one is this way, and we call it as Kekulé structures. And due to delocalization, this is the way we write it often. Okay. Now, these are called Frost diagrams. These are called Frost diagrams. This was one attempt of explaining the energies of the orbitals using molecular orbital theory. Okay. So, according to Frost diagrams, we can take benzene as a reference for aromatic compounds. Benzene is taken as the reference from aromatic compounds. And we can always distribute the benzene energy based on its structure. For example, if you have a molecule here, so I can say that a line passing through the center of this benzene like this, that can be written as the energy line, average energy line, which is called as non-bonding molecular orbital line. Okay. And any orbitals which lie below them, they are all bonding types. And any orbital which is lying above them, they are all anti-bonding type. Okay. Now, when it comes to benzene, right, based on molecular orbital theory, what we can say, all the pi bonds belong to a bonding molecular orbital. And because they are bonding molecular orbital, they are bringing extreme stability to the structure. Everyone clear? And it has all pi bonds, pi star bonds empty. There's all pi star bonds empty. So this is one attempt of explaining. The other one, the valence bond theory way of explaining is just check out Huckel's rule. If the Huckel's rule is followed as per valence bond theory, we can say it is aromatic compound. So remember, Frost diagram is an attempt using molecular orbital theory. Huckel's rule is an attempt using valence bond theory. Clear, everybody? Right. Next, check out what is anti-aromatic compounds. Anti-aromatic compounds, unlike aromatic, they are extremely unstable. Even at room temperature, they cannot be isolated. Okay. So, what are all the properties you need to look into here? Here, it should also be cyclic. It should be planar as well. There should be continuous conjugation here as well. Okay. It must follow 4n pi rule. This is not called Huckel's rule. Now you simply call it as 4n pi rule. That means the number of pi electrons should be a factor of 4n. Okay. N being any simple integer starting from 1 to 3. Now this leads to a paramagnetic nature, and there is a ring current available, but it is paratropic ring current. According to the Frost diagrams, okay, cyclobutadiene is considered as a reference for anti-aromatic compounds. Correct? So if we take this into reference here, then a line passing through these two centers that operates as the energy line or the central line, which is non-bonded molecular orbital. Okay. And then any orbital which is above or any orbital below, those are bonding and anti-bonding molecular orbital forms. And now you know that there are 4 pi electrons to be distributed. So first 2 pi electrons will go here as per Aufbau's rule. The next pi electrons, have you noticed that this orbital and this orbital have equal energy? And that's the reason one electron will go here, one electron will go here into non-bonding molecular orbital. And because the electrons are present as two unpaired electrons in non-bonding molecular orbital, remember, according to molecular orbital theory, right, NBMO has, 90% ABMO character, and only 5 to 10% BMO character. So, in all the cases wherever there is non-bonding molecular orbital, we usually refer that it has more anti-bonding nature only. So that means these electrons which are present, they will have more anti-bonding nature as compared to that of their bonding nature. Okay. So which means when you write the cyclobutadiene, so one pi bond is a bonding type. The other one is actually anti-bonding type. In a way, actually a bond exists ही नहीं कर रहा है. It is rather more like two radicals. That's it. It is existing as two radicals. And because it is existing as two unpaired electrons, it is showing a paramagnetic character, everybody. Okay, that's the reason why anti-aromatic are paramagnetic. Correct? And that's one of the reasons also, because it is not exactly a stable molecule. It is like a radical intermediate. It is unstable. And how it can get stabilized? Imagine this. Somehow, in some chemical reaction, you are able to prepare this. Imagine if you push sodium. Sodium is something which is readily going to give electrons. So it can give one electron here and one electron here. So this will become minus and minus. The minute it will become minus, what happens? Now you get 6 pi electrons. If you get 6 pi electrons, that means it has become aromatic. Got it? Or you can do the other way around also. You can react with some oxidizing agent like Fe plus 2. Correct? If you take Fe plus 2 here, sorry, I written it reverse way. Fe plus 3 here. Okay. So what will it do? It will take away this electron and this electron, consumes both the electrons, convert from Fe plus 3 to Fe plus 2. So it will act like an oxidizing agent and generates both positive charge. If you have both positive charge also, now also the ring has become aromatic. So you can see either 2 pi electrons, which is aromatic, or there is 6 pi electrons, which is aromatic. Okay. Done? Everybody? Right. Next one is non-aromatic. See, non-aromatic could be an open or a closed chain. It doesn't matter. It has to be non-planar at some segment. There should be some non-planarity at some segment. Next, there should not be any continuous conjugation. Now, this is the most important factor for non-aromatic, everybody. Rest all cases may be similar or not. Only one thing that you need to check is that there is no continuous conjugation, which means there is no circuit which is completed. So there is no ring current. You can see there is no ring current here, right? And if such a case is present, we can always say aromatic definitely more stable than non-aromatic greater than anti-aromatic. Everyone understood? Right. Let us quickly try to understand all the cases of 3-membered, 4-membered, 5-membered ring, in which case we have aromatic compounds and in which case we have non-aromatic or anti-aromatic compounds. Okay, everyone clear? Let's see. Let's start together. First case. You can see all three are sp3. There is no delocalization or anything here. So this is definitely non-aromatic. Okay. I will use this reference. This as non-aromatic. Here we use this as AR means aromatic. AA means anti-aromatic. Okay. We'll use this terminology. Next one. Here we have a pi bond, but here there is still sp3 carbon. There is no delocalization here, so it is non-aromatic. You can have one pi bond with one plus charge. Delocalization is possible. Resonance is happening throughout the ring. So this is aromatic. Okay, pi bond with minus charge. So you have now 4 pi electrons. 4 pi electrons qualifies for anti-aromatic. Now this one is non-aromatic as well. Okay, this one is non-aromatic. Now notice this compound, although this is the original look of the compound, how does this exist? The molecule will always exist in this form, minus plus with a permanent dipole moment here like this. It will exist in this ionic form with a high dipole moment. High dipole ionic species. It will exist like an ionic species. What is the reason for it to exist as ionic species? Simple. You can have a pi bond and plus charge making this ring aromatic. So keep itself aromatic. It will always, instead of this structure, it will always adapt this structure. Everyone clear it up? Right? So this is aromatic as well. So you can see this is aromatic. Okay, remember this type of aromatic compounds which are responsible for creating positive charge or negative charge on them, we call it as quasi-aromatic. Quasi-aromatic. So quasi-aromatic means where you have getting a permanent dipole. Clear? Next one, will there be any quasi-aromatic there? Yes, indeed. So we have a C double bond C. This can also be made into plus and minus and keep the ring aromatic. So here this is also aromatic as well as quasi-aromatic. Now this is again non-aromatic.
How is the third one following the 4n plus 2 pi rule.
This one, beta. Third one. See, 4n plus 2 pi electrons rule is for n being 0, 1, 2, 3, any of that. Okay. Put 0 into that. So when you put 0, how many pi electrons you are getting? 2 pi electrons. Can you see there is 2 pi electrons? 1 pi bond means 2 pi electrons. Okay. And plus charge is empty orbital. Okay. And that positive charge is moving across all three positions. So ring current is complete. All good with the first cases, everybody? Now, next line, we'll go a little quickly now. Check it out. Whichever are more easier ones, let us do that first quickly. This is non-aromatic, non-aromatic. You can see this is aromatic because you have 2 pi electrons. This is aromatic. This is non-aromatic, non-aromatic. Up to this it is clear. Everyone, please check. The next one, can you see this we can make a quasi-aromatic here because this I can make it as a plus and minus, plus and minus. It can exist in an ionic form. So plus here, minus here, plus here, minus here. By which what we can make? We can make this ring more stable. So what do I get? So this is aromatic. And what type of aromatic here? Quasi-aromatic as well. Now here also this is also aromatic and can showcase quasi-aromatic. QA, sorry. Can show quasi-aromatic. Last one, anti-aromatic. Yeah, everybody clear? See the 5-member ring case. First one being non-aromatic, non-aromatic, anti-aromatic, aromatic, aromatic, non-aromatic, non-aromatic. Okay, this is aromatic and it is definitely showing quasi-aromatic. This is aromatic, definitely showing quasi-aromatic form. Check out this third line, everybody. Did you understand the cases? Please check this line. All good with that line? So, see the next case. Now, oxygen has two lone pairs, out of which one lone pair will participating in resonance. So one here, one pi bond here, and one pi bond here. So that makes it 6 pi electrons. So remember here we have 6 pi electrons. So 6 pi electrons can make it aromatic. Okay. Here also we have 6 pi electrons, wherein the lone pair of nitrogen, here one pi bond and here one pi bond. So that makes it 6 pi electrons. So hence it is also aromatic. This is also aromatic. Same logic. Now, boron has an empty orbital and then you have two pi bonds. So only here we have 4 pi electrons. Since it is 4 pi electrons, it is anti-aromatic form. It is an anti-aromatic form. Likewise, here there are multiple lone pairs here. Every one oxygen will only involve one lone pair. So one lone pair here, one lone pair here, and one pi bond. So there are 6 pi electrons, and all of them are in resonance. But notice it carefully. Is the ring current getting completed, everybody? Is the ring current getting completed? No, right? Why? Because this is sp3 carbon. Very important to notice that this is still sp3 carbon. So ring current complete nahi ho raha hai. So hence it is still non-aromatic. Okay. Notice next case here. We have a lone pair, pi bond, pi bond. All of them are in conjugation. So here also we have 6 pi electrons and they are all in conjugation. Hence it is aromatic. Next one. We have this lone pair. This nitrogen has a lone pair. Okay, this ANH. Okay, so this nitrogen has lone pair and two pi bonds here. These outside pi bonds, lone pairs will not be participating. So again, we have 6 pi electrons here, and it is going to be aromatic as well. Next one, here there is a boron. Boron has an empty orbital. You can see empty orbital. Sorry, we have empty orbital. We have two pi bonds and one, uh, two pi electrons here and one pi electron here. So total 6 pi electrons, and there is a resonance taking place throughout the ring. Hence, this is also aromatic. So please notice this line. I hope all of you got that. Next one, benzene form. So if it is a benzene form is anyway aromatic. So this is AR, aromatic. Here sp3 carbons are there, so non-aromatic. Correct. And now notice here we have pi bond, pi bond. Now we might wonder, sir, from here it can go resonance stabilized, from here it can go resonance stabilized like this. So resonance stability can happen here. But will it make a quasi form here? That means, can it keep it like this? Suppose we have a pi bond with plus charge and O minus, or plus charge and O minus. It only be harmful because it will create this into an anti-aromatic form. So it will make it into an anti-aromatic form. So do you think it will go for an uh, quasi form? No, it will not go for a quasi form. It will remain the same. But now, should we call anti-aromatic or non-aromatic? Now, here is the interesting part. See, if it is an anti-aromatic, if it is a uh, anti-aromatic form, we expect the ring circuit has to be complete, right? But problem, what is happening? Resonance is happening from here to here. Resonance is happening from here to here. Resonance is happening from here to here. But do you see resonance happening on this location? No, right? मतलब क्या पाई बॉन्ड कभी इस पॉइंट पे आ रहा है? नहीं आ रहा है. बिकॉज ये पाई बॉन्ड इधर शिफ्ट होगा, ये पाई बॉन्ड इधर शिफ्ट होगा. So the resonance can have a movement here. Here there is a resonance. Here there is a movement. Like this, the resonance is happening, but it is not closing up. The circuit is not closed. If the circuit is not closed, what do we call it? It is still non-aromatic. Important case, everybody. Okay. Now, can we make a resonance stabilization here? Now, here I can make it. Why? Because you can see once you can get O minus, O minus, O minus, O minus, and double bond. Then you have plus, 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 and plus. So it is like one pi bond and four plus charges. So that can keep delocalizing. So due delocalization, it can become aromatic and it can show quasi-aromatic nature. Okay. Next one, benzene having any group G. Now, this group G means the G could be anything here. Any donating group, electron donating group, or any electron withdrawing group, right? Like activating groups like NH2, OH, OCH3. Okay, you can have NH, COCH3, all these kind of activating groups. Or I can have only methyl, ethyl, and these cases. Or I can even have strong withdrawing groups like all halogens, NO2, COH, doesn't matter. Whether it is donating or withdrawing, every group that is present on a benzene ring, benzene को कुछ नहीं होगा. Benzene will still remain aromatic. Okay, so every group that is present on benzene, that will only keep it aromatic. Next one, the name is pyridine. Next one compound name is pyridine. In pyridine, this lone pair is not a part of resonance stabilization. Only the inside three pi bonds will rotate. Hence, the ring has 6 pi electron cloud. So 6 pi electron cloud means it is aromatic. So pyridine is also an aromatic compound. Next, you notice this is called tropylium carbocation. In tropylium carbocation, you can see the ring size here. You have 6 pi electrons and resonance is happening all through. The positive charge can keep delocalizing at all the locations. Hence, this is aromatic. This is called tropylium carbocation. While this is non-aromatic, correct? And this is anti-aromatic, and this is aromatic, and this is also showing quasi-aromatic. How is that showing quasi-aromatic? Notice, so we can have like this 7-membered ring, keeping this as O minus and carbon as plus. Hence, it will start showing aromatic nature. Okay, and it will exhibit in ionic form. Okay, name of the species is tropolone. Tropolone. Okay, recently asked in 2025 JE only, the nature of tropolone, that it is ionic compound, it is aromatic, like that. Everyone cases are clear, right? If you go slightly ahead, here you can see you have a carbocation. If this H minus goes all the way here, so from here this H minus breaks and reaches here, so we'll get triphenyl CH, and we will get tropylene carbocation. So thus making it into aromatic form. This one set of reaction where aromatic, to attain the aromaticity, the H minus has been lost. Similarly, when you have bromine present here, instead of staying in a covalent form, it will always exist in this ionic form so that it can exhibit the aromaticity. Hence, this is an ionic bond existing. That's why it is crystalline in nature. It is an ionic solid soluble in water. Same logic here also in the second case. You can see when Ag plus has been treated with this one, you will have these phenyls intact, but here you can get positive charge. Sorry, one bromine will be there with positive charge, and this entire thing is positive charge, and AgBr will form. AgBr precipitate will form. So keeping this into, now the ring has become aromatic. SbCl5 will also convert this into an aromatic form like this with a plus charge. Now this has become aromatic and this will become SbCl6 minus, like a complex. It's a stable carbocation. Okay. Right, everybody? Next is called azulene form. Azulene is the isomeric compound of naphthalene. So here we have a 7-membered and a 5-membered ring fused with each other. Now this is the alternative pi bonds which are present in azulene. Now notice one thing. Now in this particular conformational form or resonating form, it doesn't appear like aromatic compound. But what if there is a resonance made? Pi bond is moved here, this pi bond is moved here. So you can get positive charge here and negative charge here. Now all of a sudden, now this ring has become aromatic as well as this ring also has aromatic. Why? You can see 1, 2, 3. So you can actually have a 6 pi electron cloud. And similarly, you can see 1, 2, 3. Again, 3 pi bonds here. So this will also have 6 pi electron cloud. Hence, both the rings are becoming aromatic. In fact, it will always exhibit in this form rather than existing in this form, which means we'll have positive to negative. We'll have an aromatic nature with an ionic compound nature with an aromatic species. Okay. So you can see it is a dipolar blue color crystalline structure. It is solid and stable molecule. So remember, naphthalene is dipolar 0, no polarity, but azulene is highly polar. Both of them are isomers of each other. All good, everybody? Next, cyclooctatetraene. Cyclooctatetraene is a very interesting case. You can see 1, 2, 3, 4, 4 pi bonds. 4 pi bonds and conjugation is complete. We can expect this to complete the circuit also and exhibit as you know, exhibit as anti-aromatic. But instead of staying anti-aromatic, it will stay as a non-aromatic form. Why is that? Because when you have an eight-membered ring, eight-membered rings have much flexibility. And now what you can do, these carbons can start losing their planarity and exhibit into a tub type of shape. When you put it as a tub type of shape, now what happens? The pi bonds are here like this. But here pi bonds are perpendicular to each other like this here. And again here these are perpendicular to that. Which means unless we have a parallel orbitals, we cannot have a resonance stabilization. Right? So here there is a pi bond. Here there is a pi bond. Here there is a pi bond. But you cannot make a pi bond between these two. Correct? And you cannot make a pi bond between these two. Hence, since pi bond is not being delocalized, the molecule remains non-aromatic. So remember, top shape, to avoid 8 pi electron cloud, molecule is observed to be in non-aromatic form known as tub shape. The name is COT, cyclooctatetraene. Cyclooctatetraene. Now, the planarity can be compromised only if you are getting an aromatic nature. So instead of going into the tub shape, if this pi bond can be changed into two positive forms or two negative forms, that will quickly make this ring aromatic as well as this ring aromatic. So if the aromaticity is established, then it will remain planar. So these two are planar and aromatic in nature. We will come across an intermediate benzene. In benzene also, there are 3 pi bonds. There is outside one pi bond. So outside pi bond is between two hybridized orbital, sp2 and sp2. But it has nothing to do with the delocalization inside. So here it is still an 6 pi electron cloud, hence making the molecule aromatic. Next one is being anthracene. Check out 1, 2, 3, 4. Okay. Now, these are all the resonating structures. If I have to notice which is more stable, see, the better way to look at it is you check out which one is having more benzene forms. You can see here, this one is a benzene form. Here, this one is a benzene form. And this one is also a benzene form. The last ring is not looking like a benzene form. Only two pi bonds are there. Now here, if you notice, this is a benzene form here, one. And here, this is a benzene form. This is a benzene form. Now here, only this one is benzene form. So more the number of benzenoid forms, more is the stability. That's why stability wise, you'll notice 1 and 3 are equally stable compared to that of 2 and 4 are equally stable. This is anthracene form. right, everybody? Now listen, another way of looking at, cyclic structures is this way. You always try to go across the periphery. Okay, imagine like a running track here. You are standing here and you have to uh, complete what do you say, race, and come back to the same position. So how do you go? You go on the periphery like this, like this. Now, while going on the periphery, I mean, while reaching back to this original place, here you count the number of pi bonds. One, two, three, four, five. There was one pi bond here. That pi bond can be rearranged as plus and minus. So you can have 5, 6, and one more 7. So can you see there is odd number of pi electrons, pi electron clouds. So if you have odd number of delocalized pi bonds, that means the molecule is aromatic. It will remain aromatic. So that's an easy way to visualize. Okay. If you have odd number, it is aromatic. If it is even number, it may be anti-aromatic. Okay. This is called peripheral aromaticity. Next, if you have phenanthrene, you can see phenanthrene has 5 structures, 5 resonating structures. Out of this, if you compare the stability, which one has more or less, right? So check it out. First one has here, this is aromatic ring. This is also an aromatic ring. This is also an aromatic ring. All three are benzenoid forms. All three are benzenoid forms. In here, this is benzenoid, not the center one. Here, this is benzenoid, correct? And this is benzenoid, not the center one. Here, this is the only one which is benzenoid. And here, this is benzenoid, and this is benzenoid. Clear? All of these are benzenoid forms. Okay. So based on this, what we can say? We can see the first has the all three rings being benzenoid form. So that is more stable. Then 2, then 3, then 5. And the least stable is the fourth one. This is the stability of phenanthrene cases. So you can see peripheral aromaticity in such fused cases, always check out peripheral aromaticity. So you can see 1, 2, 3, 4, 5, 6, 7, odd number. Hence it is aromatic. Now you do not worry about what is happening at the center. Here there is sp3, sp3. So at this position there is a non-planarity. But it should not matter because you should always look into the peripheral aromaticity. It is like a hat. When you keep a hat, the surrounding part is completely on the peripheral part, which is planar. So you should only see where the electrons are moving are planar or not. Okay? Clear? So hence, this is also aromatic in nature. The next type is called annulenes. Okay? Annulenes are basically monocyclic polyenes with alternative double bonds. So as long as you have an alternative double bonds, you call them as annulenes. But it should be only one ring. Okay? The ring size will keep on growing as you keep on adding extra 2 carbons. So you can see 4, 6, 8, 10, then we have 12, 14, 16. These kind of annulenes are formed. So 4 annuline means 4 carbon with 2 pi bonds. So what is this one? We know that we learned it already. It is an anti-aromatic form. Next, 6 annuline. Benzyl is a 6 annuline form, which is aromatic form. And 8 annuline, we just learned COT, cyclooctatetraene. What did we learn? This is non-aromatic. Next, the 10 annuline is very interesting one. Check out. Although it has 1, 2, 3, 4, 5, it will perfectly qualify for aromatic compound. There is one problem. During this structure, if you notice, this hydrogen and this hydrogen comes in a very close vicinity. The proximity is very close for these two hydrogens, which causes immense repulsions. And this is what we call it as transannular repulsions. Due to the strong transannular repulsions, correct? It will lose out on this planarity. So molecule which is supposed to be planar like this will start twisting this way. So from one ring, it will start moving. This is the way it will start establishing instead of staying it as one particular ring here. Okay. Hence, it loses its planarity. So it is non-planar. So hence it is non-aromatic. So now this makes it non-aromatic. So 10-aniline is non-aromatic, everybody. Likewise, if you compare even the 12 and 16 anilines are also non-aromatic. Only 14 anilines, if you compare here, 1, 2, 3, 4, 5, 6, 7. Using the peripheral aromaticity, we can say it will remain aromatic. Here we can say, sir, what about the repulsions? Well, the transannular repulsions are there, but because now the distance has increased, now these hydrogens are not in a very close vicinity. Hence, they can have very least repulsions and maintain the planarity. So it will maintain the planarity and having an aromatic nature. Okay. Everybody, out of 16 anilines, in your course only 16 anilines are there, 4 to 16 anilines. Out of 4 to 16 anilines, how many anti-aromatic we found? Only one. That is the first one. And how many aromatic we found? Two. These two. 6 and 14 are aromatic. Rest all are non-aromatic. Okay. Everybody, clear? Next. What is annihilation means? See, if you have a fused ring, correct? You have a fused ring like naphthalene or anthracene or phenanthrene and all these cases. Okay. If aromat is transferred from one ring to the another ring, that is called annihilation. Okay. That is called annihilation. For example, if you take anthracene, right? If you take anthracene here, anthracene originally has how much resonance energy? Minus 350. That means per ring, how much it is? Per ring, how much it is? Around 170, correct? Sorry, divided by 3 here, not 170. I mean, divided by 3 here. So how much we'll get? 1 and 2 and 20 means around 6, correct? Around 126. Is this clear? Approximately. This much per ring. So one ring has how much amount of aromaticity on it? Around 126 kilojoules. Benzene alone will has how much? 152 kilojoules per mole. Correct. Now see problem. Now see what is happening. The minute you introduce H2, this anthracene will consume that H at these two positions only. One hydrogen here, one hydrogen here. This way, this pi bond will move. One of the pi bond will move here with a dot and dot here. That will become a double bond. Now this ring will become aromatic. This ring will become aromatic. Of course, this ring was already aromatic. Now this ring will also become aromatic. Which means now individually we have to count. Individually, this is a benzene, this is a benzene. So this will have 152, this will have 152. So what happened? Now can you see the ring and the resonance energy per ring has increased. So per ring we had only 126. Now per ring we had 152. Per ring we have 152. Clear, everybody? So such a kind of nature where you're trying to increase the aromaticity or transfer the aromaticity further, that is called annihilation. So this is an annihilation. You can see another similar nature for phenanthrene also. In phenanthrene also, when H2 is to be added, you will add one H here and one H here. That way, both the rings got isolated. Isolated rings will always have more resonance energy. Everybody clear with the annihilation? And last thing about understanding the dipole moment and bond rotation here. So check out. So if you have these kind of multi ring structures given, joined by a double bond. So you can see these two are joined by a double bond. Now the problem with this double bond is, if at all I remove the pi bond, push negative charge here and positive charge here, then both the rings will become extremely stable because it will create a quasi-aromatic nature, isn't it? Because this ring will become aromatic now, this ring is also aromatic. That means it will establish a permanent dipole moment, maintaining like an ionic bond, correct? And will have a strong solid form. So you can see it has a high dipole more high dipolarity. It will showcase a rotational barrier, right? And that will be minimal. Rotational barrier means what? Across this double bond, if at all you are trying to rotate the molecule, do you have any energy required or it is moving freely? Now I can say it is moving freely. Why? Because it has now become almost like a single bond. Hence, the rotational barrier in this case is minimum. Same logic if you compare here also. Left side is a 7-membered ring that will become tropylium carbocation. Right side will become cyclopentadienyl carbocation. Okay, one will become carbocation, one will become carbanion. Cyclopentadienyl carbanion. Again, this will also show quasi-aromaticity, right? Because of this pi bond getting delocalized into plus and minus, both ring will become aromatic, and that will further decrease the rotational barrier. So it will become very, very small amount. While if you have this particular compound noticed, right? In this case, if by chance I remove one pi bond and make it as plus and minus, you see this ring might become aromatic, but this ring will become anti-aromatic. Hence, only when both the rings are becoming aromatic, that's when the pi bond will completely delocalize. Otherwise, no delocalization happens. Only this will remain the final product. So it will have very low amount of dipole moment. Rotational barrier is maximum here. So that means it will always exhibit a double bond character. So it is very difficult to rotate. Okay. So notice this one, rotational barrier, if it is asked in the first three cases, 1, 2, 3, definitely 3 has highest, then 1, then 2. See, between 1 and 2, you check out number of resonance aromaticity. This is a 7-membered ring versus a 3-membered ring. So which one is better? 7-membered ring will have more amount of resonance energy. Therefore, here the single bond character is even higher compared to this one. Therefore, rotational barrier is 3, 1, 2, and dipole moment is 2, 1, 3. All good, everybody? Done. So this ends about the aromatic compounds, correct? One second, let me see. Adhika, you had message bit of some. Yeah, approximately 116, right? I said 125, I guess, right? Yeah, it should be 116. Yeah, got it? So this is what you need to check out. Aromatic compounds, mainly whatever the compounds given are aromatic or not. That is the first form. Second thing, you need to check out how the dipole moment changes, which of them are showing permanent dipole, are they ionic compounds or covalent compound, which is showing quasi-aromatic nature, right? All these kind of examples you should be able to learn. Okay, right. So this ends the part one of GOC, everybody. Okay. So the second part